is roughly equivalent to the equilibrium constant. So your equilibrium constant is solved for as your products over reactants. So if we look at the concentration of products, if your Km gets bigger, we're saying we have more unbound, which would mean it's binding less tightly. Okay, so you can kind of derive it if you understand your equilibrium constant, tying back and forth. This is the 4th or 5th time teaching this, and probably the 2nd or 3rd time learning it, or not, that I've learned it before. And this is really the only first time it's starting to click on solving it from that. So I don't really expect you to remember that, but that's kind of what's going on with it. So where I believe we ended, I guess it was last Tuesday, is that we looked through each of these types of inhibitors and then how they would be interpreted, what they affect in both Km and Vmax, and then how do we plot that and what would we see out of it. Okay? There's lots of equations and all sorts of other fun stuff that we could have looked at and we kind of looked at. The biggest part that I want you to get out of it is what is Km, we'll go back over again, what is Vmax, how do they change for each of those types of inhibitors, okay? Which theoretically you could derive your way through, but it's very tricky, and I think it's a hell of a lot easier just to rote memorization in it. Okay? If for some reason you were going to become a biochemist, none of you are, you would probably want to learn a little bit more about that and where they're coming from. Okay? So we don't need that part of it. Does that make sense? Okay. So if we look at our graphical interpretations, we have 2 versions of the graph that we can go through and use. Okay, we have our standard rate versus substrate concentration, which is our standard kinetics kind of appearance. Okay, we need to be able to interpret all of our possible inhibitors off of that curve. Because that's a weird curved line and we can't interpret curved lines very well, we convert that into the straight line plot using Lineweaver-Burke calculations. So over here we have what's known as Michaelis-Menten kinetics, and over here we're looking at Lineweaver-Burke. They're both looking at the same thing, they've just manipulated the equation in a slightly different approach to interpret it. Kind of makes sense? Okay, so let's do kind of a flip back and forth, mainly because my brain isn't functioning super well this morning. So I may need to flip back and forth to remember all of these, so let's see what you guys can do. Maybe you can help me through it. Competitive inhibition. So if we look at a competitive inhibitor, what happens?
Fights for the active site.
Okay. Its definition is that it competes, so this competes for the active site. What does that mean as far as Km and Vmax go? Hold up. Ignore that, scratch that. Let's find Km and Vmax first on our curves. So we have our standard enzyme, we don't have an inhibitor, we want to know where Km and Vmax can be interpreted. Okay? So you can all cheat and look at the left one, because the left one has the answers on it, right? Where do we find Km and Vmax? The answer's on it. You just have to read the answer. Your y-intercept gives you information about your Vmax. It's not exact, it's 1 over Vmax. Okay. And the x-intercept gets you negative 1 over the Km. That one we have to watch out for because we have a negative and an inverse. Okay. I don't know about you, but that really messes with my head, and at this time in the morning, I'm probably not even going to be able to do that properly. Okay. The other way you can get it is by looking at the slope of the line. Okay. To get it off the slope, you need to have Vmax first, right? Okay. If we look at our Michaelis-Menten curve, where do we get Vmax from?
Where it plateaus.
Okay, roughly where it plateaus, somewhere up here at the top. Where do we get Km? It is half Vmax. Okay, so we can say, oh, it's this value right there. So that kind of worked. Why is that not the value for Km? It's the substrate concentration at 1/2 Vmax. So we figured out the y-intercept, or the y part of my value. I now need to have to plot that across to my curve, and now look down to the substrate concentration. That is now my Km. Okay? So your Km is equal to the substrate at 1/2 Vmax. We have to be looking at the substrate value. The substrate value is running along the x-axis. Make sense? If we now drop in a competitive inhibitor, what happens? What do you think would happen to Vmax? Think, oh, we've got an inhibitor. That should slow down our reaction. Why does it not slow it down? When do we hit Vmax?
When the concentration rate is at its highest.
When the substrate is at its absolute highest. So we have so much substrate there that there's effectively no inhibitor, which then means Vmax shouldn't change. And we should have the same Vmax. Okay? Which means we have the same 1/2 Vmax. So should we still have the same Km? No. The Km, we still have the same y value for our 1/2 Vmax. That doesn't mean the x value is the same. Okay? So we're still looking at this point, but where on that line is my Km supposed to be found? Okay, well, what happens to Km when we look at a competitive inhibitor? Sorry, you said it increases? Does everybody agree with that? Sorry, and I do apologize for this. My brain's just not doing well today. So if it increases, that means I now go over to my curve and say, okay, it increases. Let's just go crazy over here. Say there's our Km, which then means I have to connect pretty much those 3 dots, which probably means it's going to plateau somewhere off screen. Make sense? Okay? Questions about that? Okay. So we'll test you guys on it, see how well you do. What's the next inhibitor? Non-competitive. What's happening with a non-competitive inhibitor? So not the active site. And the next big one, at any time. Right. So what does that mean happens to Vmax? It's going to decrease. Because when I place in the non-competitive inhibitor, I don't care about the substrate concentration. If there's an inhibitor, that inhibitor combined to enzyme removes the enzyme from the equation. So Vmax has to decrease. So if our red was our Vmax for the standard plot, Vmax somehow decreases. I'm just picking an extreme. It does not have to be, because that looks darn close to 1/2, but it's just somewhere lower. Make sense? So Vmax decreases. What about Km? No effect. Why is there no effect on it? When can the substrate bind? At any time. If there was no inhibitor, when could the substrate bind? At any time. So there's no effect on the substrate binding. Well, what is Km? Substrate binding. Right? So because it has no effect, then we don't care. It's not going to affect the Km. So I'm going to get the exact same Km value as previous. So if that was my red 1/2 Vmax, and that's my Km, then my non-competitive inhibitor needs to be that exact same value, but at 1/2 Vmax. 1/2 Vmax for what? The old curve or the new curve? The new curve. So I have a new 1/2 Vmax. I'm looking at something like that. Make sense? So it may look weird because you're like, well, doesn't Km change? Km's not officially changing there. But because we've changed the end point, that changes the midpoint, and now everything looks like it's changed. But the Km value stays exactly the same. Okay. Which I kind of screwed up on the last one because we should have plotted it, what our line would look like. So on the Lineweaver-Burke, what should our plot look like for the non-competitive? Km stays the same. What does that mean? Which intercept? Km is located at the x-intercept, stays the same. What happens to Vmax? Vmax decreases, which means where does my curve, where's my next data point go? Why does it go higher if Vmax decreases? It's the inverse. We have to remember that. When we solve for a y-intercept, it's the inverse of Vmax. If Vmax got smaller, that value gets bigger, and our curve looks something like that. Make sense? I know I've erased it all. Can I erase everything now? Let's go back real quickly on the competitive, which I think I had in black. What did we say happened with the competitive? Increases. Vmax. No change. Which means when we look at our curve, what happens? The easy plot. The y-intercept doesn't change because that's our Vmax. What happens to the x-intercept? Km gets bigger. 1 over Km gets smaller, but since it's negative, it slides closer towards the 0, and we end up getting something along those lines. Kind of make sense? We did non already, so we're doing uncompetitive. What happens with the uncompetitive? Binds to the enzyme substrate complex only. Okay. Again, not active site. How does this affect our reaction? What happens to Vmax? Vmax will decrease. What happens to Km? Also decreases. If we go through and look at our standard Michaelis-Menten plot, if Vmax decreases, we have something lower. What does that mean is going to happen to our half Vmax? Your half Vmax also decreases. What happened to our Km? The Km decreased, which means from our old Km, I guess I got to put all those stupid lines on. Where's that half Vmax? So ballpark, there's the old Km. The new Km needs to be somewhere underneath that. I'm not the greatest drawer, but as long as we have the points down, we should be good. Make sense? And I didn't put it on the other curve again, did I? Nab it. Hey, look at that. Undo. Beautiful. Okay. So how do we put that or plot that onto our Lineweaver-Burke plot? Vmax decreases, which means the y-intercept will increase. Km decreases. If Km decreases, 1 over Km gets larger, but it's a negative value, so it gets further from the 0, and it ends up hitting somewhere out here. The interesting feature of this is that God, that was a horrible straight line. Is it changes linearly, or perfectly with the previous one, so you get parallel lines. Okay? Kind of makes sense. Okay. The last one that is particularly relevant for the homework, we'll look at here in a second, would be the mixed uncompetitive, or not, it's mixed non-competitive. Of course I would get it wrong. Which means what? So number one, not active site. What's that?
The enzyme can still bond, right? You mean the active site.
The substrate could bind. So maybe it's affected, maybe it's not. Okay. That messes with how we go through and interpret everything and what happens to Vmax and Km. What's that? I don't know that I accept that. It's hard for the Vmax to increase because you're saying your reaction is going faster. Adding an inhibitor and having it go faster doesn't sound right. So what you might be thinking of is what happens to Km. The Km increases. So what does that mean? If Vmax decreases, our y-intercept increases, our x-intercept it's always weird to say decreases as a negative value. Closer to the zero is probably a little bit of a better statement. And we end up saying something along those lines. Okay? Kind of, sort of. So, memorize what they are, how that affects Km and Vmax, and then know how to plot those. Okay, you will get asked all stages of that. Okay, and that can show up both in multiple choice and in show your work. The show your work will typically be drawing on a line. The multiple choice ends up asking probably more along the lines of a competitive inhibitor is which of the following statements is true. It binds the enzyme substrate complex. It binds, coming up with some kind of random statement. Kind of make sense? Okay. With that said, we also have the homework. And if you've done the homework, you've probably seen this. It's the very last question in chapter 6. And you get these two curves, and then it asks you to interpret those curves. So when you look at those curves, what do you see? What do I want? That button? Cool, that worked. Because this is a way to ask the multiple choice. I could give you the curve and say, what type of inhibitor is this?
So the first one
Okay. I'm hearing uncompetitive for the first one. And the next one is mixed. That's really what I expect you to be able to do. Okay. With some kind of minor caveats, we'll look at the next scale of difficulty on that. But you're labeling what type of inhibitor it is based off the data that you see. Okay, so you know something, can you interpret the graph and how that matches? Make sense? Okay. So if we then, let's see, where's my mouse? There it is. Can I scroll? Probably not. I did escape. Go away. Okay. Yeah, a couple of years ago, what? Yeah, I agree. Okay. Theoretically, you should be able to complete the algebra to solve for 1 over rate versus 1 over substrate concentration and see what term, extra term, is now either affecting Km or Vmax. Okay. Just algebra, it's easy. It's not that easy. But it is just algebra. Okay. I don't expect you to do that algebra. Okay. So kind of click your way through it. What I will do is grade it by hand after you've all submitted the homework assignment. I'll go back in and be like, you tried up here. Theoretically, you're not trying more than how many times? 3 up here because there's only 3 choices. So you should be able to go through and figure out the correct answer for that set of the question just by kind of clicking your way through. Some people have looked at it and said, well, there's some copying of the equations across. So if you recognize one equation, you've now eliminated the other equation, and you can simplify that down. Okay? I don't really care how you do it, but just get that part right, ideally, because that'll make it a little bit easier for me to go back in and grade. Okay, or grade by hand. And all I'll do is just give you credit for that. So anything you missed, I'll just give those points back to you. Okay? The part where you will actually lose points would actually be down here. What are they making statements on down here?
Mechanism.
Yeah. Where we had started with this question and we said, well, one was the mixed and the other one was the uncompetitive. What are they providing down here? The definition of what mixed is, the definition of what un is. You should be able to answer this part and get that part correct. Okay? And if you don't, that's okay. That just means you need more practice memorizing the parts and recognizing those pieces. Does that make sense? But this part I will grade. That crazy equation thing, I'm not going to touch. Okay? Because I very admittedly have a very hard time with that. First time I taught this, I had a student that just looked at it and was like, that's the answer. And I was like, you're just guessing. He's like, no, I'm not. And he showed me. I was like, you suck. That's just not even fair. Okay, so let's see if I can... Questions on that? Of course, it's not going to do what I want it to. Oh, there it went. Okay, now I'm back. But I jumped like 5 slides. So, we roughly okay with chapter 6 then? We've got a lot of kind of memorization, looking at those pieces, how those pieces interlock, and what those definitions are. Okay? But that's what I expect you to get out of it. We move into chapter 7. Chapter 7 brings in this concept of kind of mechanisms to a certain part. Okay? I've listed a whole bunch of kind of key words because it's really easy to get lost in what's happening within chapter 7. So you should recognize these key words and be able to trigger off of them. Okay, so we've got allosteric, which we've already talked about, feedback, which we'll talk about, pathway, which is just how a reaction works, homo and heterotropic, kinases, proteases, coenzymes. Okay, we'll look at some actual enzyme modeling to a certain extent, some kind of interesting effectors. So we can look at phosphorylation and zymogens. What are those? So if an enzyme gets affected, we've got a couple examples. Phosphorylation can be something that can affect them. We can also hear something about zymogens and what those are. And then we'll look a little bit at the organic chemistry behind chemical reactions or behind an enzyme reaction, particularly chymotrypsin. So to start it off, feedback inhibition. Okay. If we take a look at this reaction, enzyme 1, enzyme 2, enzyme 3. So it's a pathway to go from A to D. Okay. And if we looked, or what we will look at in the next unit, is all of the kind of metabolic pathways that we can see, which is a fascinating thing to look at. You'll see a string of structures, a string of enzymes, and how those enzymes potentially function to shift those structures. So we have a pathway that moves along. Okay. If I start with A, and I'm making D, okay, does that mean every time I see A, I immediately turn it into D? Okay, why not? A may have other uses, and I want those other uses to go somewhere else. Okay? So each of those stages has a control feature associated with it. Maybe too much D is a problem. Okay? So, I see people laughing already. Too much C is a problem. Okay? So we need to come up with adjustments. You guys are horrible. We need to come up with some way to affect the reaction and prevent it from working. How could we do that? Well, we could put in inhibitors. An inhibitor will shut down the reaction. So do we want a new inhibitor? Do we want another thing that can contribute to this? Well, maybe. Okay? Or maybe we want the product to actually inhibit. So maybe the process of forming C, excess C comes back and it binds to enzyme 1. If it binds to enzyme 1, it somehow shuts down that reaction. What does that mean happens the concentration of C? It's going to decrease or maybe stay constant, okay? Because it's no longer being produced. So what we're seeing in that is what's known as a feedback inhibition. The product of a later stage comes back and it prevents the action of an earlier stage. Okay? That's all I really have to say about that. That's feedback inhibition. Super exciting. Okay, so let's scale this into the next thing. Okay, enzymes with allosterism. When we talked about allosterics, we saw that with hemoglobin. Hemoglobin had that sigmoidal curve. Okay, the whole point of our kinetic section is to be able to explain using equations and come up with various terms, Kmax or Vmax and Km, descriptors of the enzyme, so constants. So I can then say, this gives me some information about the characteristics of that enzyme. But that only works if we have a hyperbolic curve. What's the issue with allosteric enzymes? They're sigmoidal curves. They don't match the kinetics that we would describe on a Michaelis-Menten and then eventually Lineweaver-Burke plot. So we have to manipulate and change how we understand these, and that manipulation can be a bit nuanced. Okay? So to start off with, we have two possible effects. We could add something that inhibits. Well, we've seen that. It's an inhibitor. Okay? We could also add something that promotes. Okay? We could add something to the enzyme that now makes the enzyme go, hell yeah, give me more. Okay? I can do more work. So we have two effects when we're looking at your curve. You've got an activator, which is a positive effect on the reactivity of the enzyme, and you have a negative effect, which is your inhibitor. Okay? How do those things affect your overall enzyme function? Well, there's two things that describe our enzyme function, Vmax and Km. So depending on what our effector is doing, if it's affecting Vmax, we can refer to it as a V system because it's affecting your rate. Okay? Or we can refer to it as a K system because it's affecting, not quite concentration, our binding constant. That's our Km. Okay, so that's the two systems that we're looking at. We do run into a bit of an issue here. Vmax is easy. Vmax is just where the thing plateaus. All of our enzymes are going to do that. What's the issue with K, particularly Km? Km was solved by solving Michaelis-Menten enzyme dynamics. Is this Michaelis-Menten anymore? No. So we don't officially have Km anymore. What did that M stand for in Km? Michaelis-Menten. If we're no longer Michaelis-Menten, that Km can't hold true. Okay? It's got to become something else. Okay? Well, when we looked at Michaelis-Menten, how could we solve for Km? We could plot it as a straight line. That's assuming we have Michaelis-Menten dynamics, and that's not going to work out nicely for us. There was another way we could do it. We didn't have to have a straight line. Half Vmax. We look at Vmax, we go half that, the substrate concentration at that value gets us our Km. Okay? We can still define that term for a sigmoidal or a allosteric enzyme. We can't, however, call it Km anymore because it's not Km. The M is Michaelis-Menten. It's not Michaelis-Menten enzyme dynamics. So what do we end up calling it? K.5. Because it's the substrate concentration at 1/2 Vmax. So for all intents and purposes, it is solved for kind of an identical pathway as we did for Michaelis-Menten. We can't call it Michaelis-Menten because it's not Michaelis-Menten. Okay? So they had to invent a new term for it because it technically is not the same thing. Kind of makes sense? Okay. We already went through and solved this. Should we go through and do it again? Okay. So your Km and K half are effectively the same thing. It's just saying what happens when we're at 1/2 Vmax. Okay. So allosterism is again the changing of your shape of your enzyme. Okay. We now run into an issue of mechanism. How does that change in shape affect our reaction? Not only how does it affect, but when, which is really a primary concern with mechanisms. Okay? When the inhibitor binds, does it immediately shut down activation, or does it bind and then slowly something happens that prevents enzyme activity? Okay? This can be tied back to organic chemistry, and with our simplest of, or typically, not the simplest, the first sequence typically of organic reactions you learn as an S substitution. We had two mechanism types. They were SN1 and SN2. SN1 took how many mechanistic steps? Everybody says that. It's 2. Okay. The 1 does not stand for the mechanistic steps. It stands for the amount of reagents in the rate-limiting step. Since there's only 1 reagent in it, that's why it has 2 steps. Okay. So SN1 happens in multiple steps. SN2 happens in 1 step. All the reagents come together in one big thing. Everything coming together in one big step can be referred to as, we take the violin, the flute, the drum, trumpet player, put them all together. Give me another word than orchestra. I didn't think of that one. They all come together and play for you.
Symphony.
You'd be going to frick. Concert. We have the concerted step, or the concerted mechanism. Everything's happening at once. Okay? So the inhibitor or the activator binds and immediately changes the enzyme so that it either increases affinity for the substrate or decreases affinity for the substrate. And we have the concerted mechanism. Okay? That would be roughly equivalent to the SN2 mechanism. Okay? The sequential, the inhibitor binds, the enzyme thinks about it and says, yeah, you know what, I'm going to change my shape now. Changes its shape as a secondary step. That change in shape prevents the substrate from then binding, or enhances the substrate binding. Okay? So those are the 2 types of steps. Okay? Both mechanisms then need to get centered around some kind of understanding, and that's what we're looking at with these 2 images. Okay? You'll notice that they've got that little squiggle through the middle of it. We're looking at 2 halves. Why would we have 2 halves? Kind of 2 enzymes. I don't quite accept that. That gets better. We have 2 active sites. Why do we need 2 active sites? Because we're looking at increasing or decreasing activity. We will have multiple active sites in these kind of enzymes. Okay? Very least multiple binding sites. So we're looking typically at least 2 halves. Okay? One of those halves will not bind substrate. Okay? So we could call that the not substrate binding one. Okay? That's an awful lot of words. Okay? So we could try and simplify that to unsubstratable, because we like inventing words. And then we could call that thing, because unsubstratable is a really long word, we could just simplify that down into a single letter. And we could call that U. And of course, we decided to not call it U, we decided to call it T for taut. Because when I think unsubstratable, I think taut. Okay? Maybe it's German, I don't know. Okay? So we have the formation of the enzyme that does not bind substrate is referred to as the tight or taut version of it, okay? Which does get simplified all the way down to T. Okay? What if the enzyme is now activated so that it can bind substrate? Well, it's now not tight or taut. And what's the opposite of tight and taut? Loose. Man, you and coming up with synonyms. Relaxed. We have the relaxed form, and in the relaxed form, I can bind substrate. Okay? So we end up with two forms of the enzyme. The tight enzyme, or the taut enzyme, which doesn't bind substrate, we'll call T. The relaxed form, which can bind substrate, we'll call R. The enzyme can convert between those two states. Because it can convert between those states, and it's in an equilibrium between those, we can then also define an equilibrium constant, which would be our products over our reactants. So we would expect the concentration of the taut form divided by the concentration of our relaxed form. Okay, products over reactants, make sense? The symbol we use for concentration of products over reactants is, okay, thanks for not looking at the slide, capital K, an equilibrium constant. We'd be like, it's an equilibrium constant. We can describe our enzyme using that. We can call that capital K sub E for enzyme activity. And instead, what do biochemists go through and do? They invent yet another letter term that we could go through and apply it, and we end up with the term L. Because what comes after K? L. And I can almost guarantee that's why they picked L. Okay? So the balance of looking at your tight form versus your relaxed form, which one is more prevalent, is known as L. Okay? It's roughly the same thing as your equilibrium constant, because it's not officially an equilibrium constant. Can't really call it that, which is why they switched it up. Okay? But that's roughly what it is. If L gets really, really large, what does that mean? I lied. If L is really, really, really small, what does that mean?
R is big.
The concentration of R is very, very large. Okay? R is the relaxed form. That's the one that can bind our substrate. So if L is small, what would we expect to happen to our rate? Should go up. The enzyme is now active. It can react with the substrate. Okay? So by looking at some of these terms, we can start to apply how we would see that affect further on down the road our mechanism or our rates. Okay? So what they've shown here is L is very, very large. Well, if L is large, that means T is bigger than R, which means I'm in the unsubstratable form. Okay? Why did they specify L as large and not L as small? Typically, our enzymes are in their inactive state. Okay? We only want enzymes on if they're functioning. Most of the time, the enzyme is off. Think about lights. Okay? The lights in your house. How often do you leave the lights on? All the time. Theoretically, you don't, because you're green and you save energy. Okay? We turn off those lights because we don't want to waste that energy. We only turn them on when we need that light. Same thing's kind of happening with our enzyme. So the standard state is that we are looking at a very high concentration of our enzyme in the taut or inactive form. Okay? That's why they're giving you L as large by default. Kind of make sense? Okay. So, R, our substrate binds tightly. T form, the substrate does not bind well. Okay? Notice there's an extra term up there. We've got the native form. Okay? We said our enzyme starts in kind of the taut, non-binding state. Okay? Well, that's where it naturally exists, so we can refer to it as the native form. Okay? In the taut form, inhibitors do bind well. Okay, because what's the role of an inhibitor? To prevent the reaction from working. Okay? So in the taut state where I'm not active, that's where I would expect inhibitors to bind, to keep it in the taut form. What happens if I go over to the relaxed form? Would I expect inhibitors to bind very well? Probably not, because what do I want to bind? The substrate. Okay? And we've got one more large thing we can bring in here. We get this C. Okay? C is the ratio of your dissociation constants. RS, TS. What is that? What is RS? The relaxed bound to substrate. So the substrate can still bind to each of these, both the taut and the relaxed, but it doesn't bind very well to the taut because the taut shouldn't bind it. That's its whole goal, is to not bind the substrate. Okay? So we can define this extra term, C, as the kind of, they're kind of our Michaelis-Menten constants, our binding constants for the relaxed form over the taut form. Okay? Because it's not confusing to look at that, which was a joke. Okay? So we have L that we can look at, and then we have this new term C that we can look at. Okay? And they're both going to affect how our enzyme binds and changes its situation. So let's see what happens when we change L. As L gets really, 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 really big, what happened to the curve? Becomes more sigmoidal. Meaning what? More what? Kind of allosteric. I'm actually blanking on the word right now. Hemoglobin is, myoglobin isn't. What's that freaking word? Oh, I got it. Cooperative. When we bind one oxygen to hemoglobin, what happens? It increases the affinity for more oxygen. Okay? So as L gets larger, we become more and more cooperative in our binding. Okay? Which makes it more and more like an allosteric enzyme. The less large L becomes, the more hyperbolic it becomes, and the less allosteric, the more like a normal enzyme. So if we went back and looked at a normal enzyme, remember we're looking at the balance between the taut and the relaxed. A normal enzyme has which form, taut or relaxed? Normal enzyme kinetics, not allosteric. It should just be in the relaxed form. And there are some enzymes that don't have a switch, they're just on all the time. Okay? So our normal enzyme kinetics, the relaxed form, is what we have. The substrate binds. It doesn't change to prevent or it doesn't change to increase affinity. So we only have the relaxed form, which means L effectively becomes 0. We'd only have the relaxed form, we'd be at exactly a hyperbolic curve. Okay? As we start to increase the taut concentration, we have less and less active enzyme. What happens to the rate if I have less active enzyme? It goes down. What happens to the curve at the front as I have less and less active enzyme? The slope flattens out right at the beginning. Okay? Giving me the characteristic S shape. Kind of get it? What's happening with C? And this one always breaks my brain. Okay? So if C is 0, what are we saying? KT is large, KR is small. What were those? Yes, constants. Give me more than that. Can we apply this? I'm trying to track through the mathematics in my head, and that never works well. Those are effectively our binding constants for each of those. So if we say KT is large, or sorry, C is small, we're saying KT is large. Okay, which means what is the binding affinity for our taut with the substrate? Careful.
For the inhibitors to bind?
Remember our K. What was our K? Because this is now looking at our inhibitor, yeah. It's saying it doesn't bind. This goes back to the question that you asked at the very beginning of the class. RKM. Okay, what was RKM? It's effectively the dissociation of the enzyme and our substrate. If KT is very, very large, what are we saying? It's not binding. Okay? There is zero affinity with the top form. What does that then mean?
Dissociation.
It dissociates a lot. Okay? Which then means our Kr is a strong binding affinity, so it's a small value. Okay? That small binding affinity is going to do, our small binding affinity, which means small value, large binding affinity, okay, means what? Does it release to form products? No. So what do we see as our observed rate? Slow rate. There's no product formation. So what happens with our curve? It slows down and we have more of a sigmoidal curve. As we start to play with that C value and change that ratio, notice that we start to become more and more hyperbolic. Okay? So the smaller your C value, the more sigmoidal, the more of a cooperative effect you can build. Right? And that goes back to what those K values are in understanding kind of their dissociation and all of that being, of course, inversely related. Okay? Do you need to derive it? No. You need to memorize it. Okay? So what I would do is say, okay, C, small, meant sigmoidal. What was C? The balance of R to T. The equilibrium constants of those, the binding affinities. Okay? L. Small l meant hyperbolic. Large L meant sigmoidal. By tying it back to what the shape of your curve is, you can then tie through both the relaxed and taut forms and kind of approach what's going on within those.
So I'm confused about it. So Km, Kr, and Kt are all binding constants?
Yes.
And the higher the number, or the higher the value of that, then that means it dissociates more. So there's not a strong bond between whatever.
Yeah. So it comes back to what our K is. It's the roughly equivalent to enzyme substrate over the enzyme substrate complex. The larger K becomes, the more free stuff you have, the less bound stuff you have. So the bigger K means less binding.
And that's true for all three.
It's true for all three. Okay? So, what happens in the concerted state? Okay, we still have the balance between our relaxed and our taut form. That's still oscillating back and forth. Because it's all happening at once, when the substrate binds, where does the substrate bind? Can it bind to the top? No. It can only bind to the relaxed. What happens when it binds to the relaxed? What happens to the concentration of the relaxed form? It decreases. It's been removed from our enzyme reaction. If it's been removed, what then happens to that equilibrium? It shifts to form more relaxed, which means we've got a balance between our inactive and our active form. They're sitting there happy, back and forth equilibrium. Substrate binds to the relaxed. There's now less of the free relaxed, which then means we need to make more of the relaxed. So what happens? The top form changes conformation, forms relaxed. Okay? Which then means I have more active enzyme. Our reaction can slowly start to build. More substrate binds, then what happens? That's removed, more taut forms, which means what happens to the curve? I end up seeing it slowly pick up, and I get that sigmoidal effect. Okay. Kind of makes sense? What if we don't have any of the top form? Well, there's now no equilibrium here. Substrate just binds, which means hyperbolic. Okay. Because we have such a high concentration of the taut as our standard state, okay, we have very small concentration of the relaxed. The substrate binds, and that removes it from the solution. We have to form more relaxed. So the more our substrate reacts, the higher the concentration of substrate, the more I end up pulling relaxed out of solution, causing the top form to come across. I now have more active enzyme, which then means I can pick up the rate faster. But I have to reach a critical amount of substrate to be constantly pulling that enzyme out of solution. Sort of out of solution, out of the equilibrium. Kind of makes sense? What happened, conversely, if we added an inhibitor? What does the inhibitor bind to? The top form. But if I bind an inhibitor to the top form, I don't have the top form anymore. I have the inhibitor top complex. So what happens to the concentration of the top form? It goes down. What does the equilibrium say? Shift to the right. We end up losing relaxed form when the inhibitor comes in, and it starts shuttling more over to the top form. Okay? So when we're looking at the concerted mechanism, we're saying the substrate affects the relaxed side, an inhibitor affects the top side. How does that overarching equilibrium get balanced out? Kind of makes sense? It's kind of neat. I mean, in kind of a weird sadistic sense. But that's what they're going through and looking at. And we could then go through and look at all sorts of other effects. Activators. Okay, what happens if we add in an activator? What would the activator do? Well, the activator should bind to the relaxed form. When it binds to the relaxed form, what happens to the relaxed concentration? It goes down, which then means taut has to replace it. I get more active enzyme present in solution, so the rate speeds up again. Okay. What happens if I have tons of activator present? So we ignore the presence of substrate. I just add in a crap ton of activator. What happens to the equilibrium between the relaxed and the taut? It shifts where?
It shifts left. Because of the activators, it's going to speed up. And so
You guys are saying left and right, and it's the whole inverse thing. Yes, it shifts left to form more of the relaxed, which then means before I even add in the substrate, what is the ratio of relaxed to taut? Careful. You said it shifts more to the left, which then means there's more relaxed, less taut. What would happen to my curve? Hyperbolic. As I add activator, what happens to the curve? Oh, it became more hyperbolic because I'm looking at the balance between the relaxed and the taut. Kind of sort of makes sense? At least I kind of think that makes sense. Okay? The inhibitor is going to do the opposite thing. So it's looking at how those curves get shifted based off the mechanism and how our activators or inhibitors are working with the relaxed and taut forms. Okay? The sequential mechanism. The reason the sequential mechanism was invented was because of this fancy word, cooperativity. Okay? As we bind something, it allows for more binding. If we look at the concerted mechanism, it's not really allowing for more substrate to bind. It's just allowing for more relaxed form. More relaxed form means a higher rate. Okay? In the case of our cooperativity, what happens when the substrate binds? Okay, so notice, what is it binding to? The taut form, the inactive form. The substrate comes up to the inactive form and says, "You are taking me." It binds. The taut form is still like, "Oh, what's going on here?" And I say, "Fine, if I'm going to accept you, well, I have to change my shape." Changes its shape to now the active relaxed form. But half of the enzyme is still in the top form. This is why we have that line. But because it changed its shape to the relaxed form, what happens to now the other top form? Changes its shape into relaxed form, meaning more substrate combined. So what kind of an effect are we seeing in that top one as far as a cooperativity? Is that a positive effect or a negative effect? It's a positive effect. As we bind substrate, we can bind more substrate, and we have more active enzyme. What's happening in the bottom case? The inhibitor comes in and binds. Okay? We get a conformational change. Okay? And this gets weird. We look at the conformational change. It's staying taut all the way through. But if we jump to the very end, what ended up happening to our binding site for where the substrate would bind? It changed further from where it started. It changed. Well, they didn't do a very good job of showing that drawing. They kind of did. So here we have the form where our substrate could bind. Inhibitor binds. Now what happens? That top form affects that top form. That top form changes. And now we have very low affinity for the substrate. Okay? So we have that kind of sequential step. The inhibitor binds, goes, oh, now, yeah, fish that I can't bind substrate anymore. Thanks, let me let the rest of the enzyme know that we can't bind substrate anymore. Rest of the enzyme, oh, I'm not allowed to bind anymore. Okay, let me change my shape. Okay, and it changes its shape to now say, whoop, substrate, you can't bind anymore. Okay, you can't force yourself in here. We've now changed the structure enough that you can't physically fit. Okay, so in this case, what do we now have? A negative cooperativity. We bind something and it prevents it from binding our substrate. So the sequential mechanism gives us that. The concerted mechanism doesn't. We're still oscillating between the taut and the relaxed form. It's just how we get between those. The concerted, to me, is a little bit easier to understand, maybe because I don't like but understand equilibrium. And we're looking at an equilibrium effect between the taut and the relaxed form. It's relatively straightforward there. We're pulling it out, we're putting it in. And the sequential, we're changing the structure of the enzyme that then kind of makes a cascade effect further on down the line. Okay? In all cases, we end up coming back to, and I have a feeling it's not on this slide, the balance between our L, taut versus relaxed, and our C, the binding affinity of our relaxed versus our taut. Okay? So we can represent those and look at those effects and how they affect our plots. Kind of make sense? Okay. Then we move into kind of our more just now factual stuff. Okay? Phosphorylation happens to be a very common metabolic pathway to either activate individual reactions or shut them down. Okay? So why would we expect phosphorylation to be involved? Okay, we have briefly talked about a big reason why. What is the energy store currency? ATP. And ATP goes to ADP, releasing phosphate. There's lots of phosphate floating through our cells, okay, and ATP can be used to mark an enzyme or mark a substrate to say, hey, do something here. Okay? So because we use phosphates as our kind of our energy currency, we do see a lot of phosphorylation affecting our enzyme reactions. Okay? So either putting phosphates, it's typically putting phosphates on. Okay? So it's one of our primary reasons. What we'll also notice is that when we look at phosphate, and we'll see this when we look at the energy effects in the third unit, okay, there's some pretty massive structural changes when we put a phosphate on. We take a look at serine versus phosphorylated serine. What's the big difference that you see? I don't like you saying hydroxide, but I know where you're going with that. We've got a hydroxyl, which becomes not hydroxyl, meaning what changed? what force can you see coming out of the hydroxyl? Yes. Hydrogen bonding. Versus the phosphate, do we have hydrogen bonding anymore? No, what force do we have? So covalent isn't a force, that's a bond. And I would question that statement. So yes, there is a dipole because we have electronegative oxygen attached to a less electronegative phosphorus. This is where biochemists and organic chemists tend to get a bit annoying. What was kind of implied out there? A charge, meaning what is the force we're seeing? Ionic. We have what, a weaker force or a stronger force? A stronger force. Stronger force means more attraction, which means more reactions. Right? The presence of that phosphate, just by changing kind of our intermolecular forces, immediately starts to mark that as saying, let's do something, chemistry there. Okay. What amino acids do you think would work on this? Don't tell me serine, that cheats. You all memorized all 20 amino acids, right? By the way, I don't think I told you this. I looked at the advanced OChem, like there's the next level up and then the next level up, or biochem. I looked at their test. It was roughly the same as ours, except 3/4 of it were, did you memorize your amino acids? So I felt kind of nice about it. We're mimicking. We just aren't doing that stupid step. It's not stupid. I shouldn't say that. Which amino acids would be likely prone to that activity? Why aspartic acid?
Because of the forces.
Kind of accept that. When phosphate reacts with our serine, we're roughly getting the oxygen attacking the phosphorus. Those of you that took, you all took OChem, so you should be able to tell me this. Oxygen will act as an electron donor from our amino acid, attacking the electropositive phosphorus because phosphorus is bound to a whole bunch of electronegative elements, and it can then kick out water as a decent leaving group. For this reaction to occur, what must this amino acid have? Electrons. What amino acids have lone pair electrons? Okay? So a lot. Okay? Serine works, threonine works, cysteine works. Okay? So it's looking for amino acids that have those lone pairs that could be donated out to react with our phosphate. Okay? So it's kind of trying to recognize those patterns. Okay? Will they only act as activators? They could act as deactivators as well, but realize what's happening is we're increasing the affinity, we're increasing some reactivity here. More than likely, they'll be falling under the activator category because we've made it more reactive by putting in that charge. That isn't always the case, okay? But that's kind of what's happening here. Okay? Kinase. Kinases is an enzyme name that applies to things that catalyze the transfer of a phosphate. Okay? Is that something you're officially responsible for? Yes. Much the same way you're responsible for having to have memorized your amino acids, sort of. Okay? There are certain enzyme nomenclature rules that you're responsible for. You will hear kinase pop up a lot. So when you hear the word kinase, you should immediately be saying, oh, it's transferring a phosphate. What is it transferring a phosphate to or from? That'll come from the rest of the name of that kinase. Okay? So you'll have this big long name, and at the end of it says kinase. You go, ah, I'm transferring phosphate. Okay, so it's just recognizing the patterns that, albeit very few patterns, in enzyme nomenclature. Okay. Zymogens. So if we take a look at chymotrypsin, we take our chymotrypsinogen. Notice it ends in inogen because inogen. Where did it go? Oh, there it is. What does zymogen end with? Gin. What does chymotrypsinogen end with? Gin, because they're referencing the same concept. Chymotrypsinogen is the inactive form of the enzyme chymotrypsin. Remember, we talked about chymotrypsin as an active enzyme and what it could go through and do. That was cleaving, what do we say, the carboxyl end of phenylalanine and tyrosine, I think. Did I write that up there? So we'll just assume I'm right because no one's challenging me. Okay? So chymotrypsinogen is that inactive form of the enzyme. Okay? So what has to happen? Well, something has to come through and make it active. How does it get made active? Something comes through. We take a look at our chymotrypsinogen. It becomes pi chymotrypsinogen. What changed? They don't show that really nicely in that picture, do they? Oh, yeah, they do. I just didn't see it. What happened? We broke it. Okay? We have this big, long peptide chain. We go through and we go, cut. What happens when that cuts now? Can this part move more? Yes. And the process of it moving more, what is this yellow line referencing? A connection between an amino acid over on this piece and an amino acid over here. Okay. So it was initially connected in two places, hence it was cyclic. We cut that cyclic structure open, and now that piece can free float. That free floating piece comes back around, sees that 17 to 148, and says, hey, I can cut you. So it cuts that, and it cuts the 14 to 15. What then happens? We now have three pieces. Again, what are the yellow connections? They're side chain interactions causing those pieces to now be linked to each other. What do we now have? We now have our active enzyme. Okay. The zymogen is just saying we have an inactive form of an enzyme and it needs to get adjusted somehow to form the active form. Okay. That somehow needs to be an active bond cleavage. So we start with our zymogen form. An enzyme comes in and says, hey, you need to be activated. I'm going to cut something. We did a quick cut. That now changed the enzyme because it changed its structure. That structural change was enough to change it into a more active form, which was able to self-catalyze. It could go back and actually cut itself apart. By cutting itself apart, it then converts into the fully active form that can now go do anything else or do those same properties on something else. Okay? Kind of, sort of. These types of enzymes are typically referred to as proteases or caspases. Okay? Protease is your protein ace or protein eater. It's kind of the way I'm looking at it. Okay? Which then means it's a digestive enzyme. It's an enzyme used to cut up other proteins. Okay? Your caspases, same deal. So if you're looking at the name of something, say chymotrypsin protease, oh, well, that means that enzyme is designed to go eat chymotrypsin. Okay? Active site chemistry. What's going on at the active site? So number one, we've got our primary structure, the sequence of amino acids. Okay? What are the intermolecular forces coming off of those amino acids? How do those affect how the substrate can bind? Secondary, okay, and larger structures. Not just the sequence of amino acids, but how do those amino acids fold around each other so that we can say get maybe amino acid number 2 next to amino acid 43. And when they get close enough to each other, they create, the active site. So really what we're talking about is organic chemistry. How does the enzyme organize individual amino acids to facilitate doing a catalytic reaction? So this is really going back to organic chemistry. Okay, so we will look at that in just a second. Specificity. all of our, or most of our amino acids, how many of them, in just a second, are chiral? How many amino acids are chiral? 19. What's the not? Glycine, because it has 2 hydrogens. Its R group is an H. There's no chiral atom. Okay? Which means most of our proteins, if not all of our proteins, are chiral. Which then means they react differently with other chiral species. Okay? Think about your hands. We have left-handed people in here? Yeah. How do you like cutting with right-handed scissors?
I'm used to it now.
Used to it now. So you didn't like doing
You
it.
don't really have the option.
Yeah, in most cases you don't have the option. So you just have to learn to deal with the pain. Okay? Enzymes don't have to learn to deal with the pain. They just say, screw you, I'm not going to touch it. Okay? I'm just not going to cut things. Okay? It needs to fit, otherwise I'm not doing it. So if we take a look at most of our molecules, we've got different binding pockets. This is a horrible picture, guys. Okay? Yeah, what were they even trying to do? I could do a better drawing than that. I'm going to make it better. We've got a square peg there, and we have a square peg here, not a cylinder. Okay? If square, circle, triangle, if I alternated, say, the circle and the triangle, circle and the square here, that then would not be able to bind into the active site. Okay? For those of you that don't believe me, go ahead and find yourself a pair of left-handed scissors and use those with your right hand. Let me know how it feels. Okay? So because our molecules are chiral, those active sites really change and inhibit other different reagents from coming in. So if we went through and used chymotrypsin as an example, okay, we've got the catalyst of, hey, look at that, I was right, phenylalanine and tyrosine, okay, catalyzing that reaction. So we could go through and look at the primary sequence, what amino acids are critical to that reaction. Okay. That gets a little bit tricky because the amino acids are not all in a line. Okay. Those amino acids can be further on down the chain. So how did the secondary structure or the tertiary structure adjust to get all those amino acids next to each other? Okay. We can then go through and say, well, how does this work? Okay. Which amino acids are critical? Well, I can go through and say, well, there's 50 amino acids in this sequence. Amino acid number 1 was serine. I'm going to make it threonine. Does it still work? Yeah? Okay, well, it doesn't matter. Serine versus threonine, I don't care. I'm going to leave it serine. Amino acid number 2 was histidine. I'm going to make it threonine. Does the enzyme still work? Yeah? Okay, well, I'll go back to histidine. Amino acid number 3, I'll change it. And eventually, I'll find the amino acids that change the function of the reaction. Now that I know that those are critical to the reaction, I have an idea of what types of chemistry they have, okay, and that they must be involved in the active site, or likely involved in the active site. Okay. I can then go through and label them. Okay. Those tags give me some more information. So it's now a question of how do I scaffold all this information to then determine not only what the sequence is, but then what are the important pieces. Okay? A lot of this comes from just not knowing the structure. So one of the things we find out is serine 195 and histidine 57 are critical to the activity. We change those, enzyme doesn't work. Those have to be there. Why? Cliffhanger. We'll talk about that Thursday.